Okay, for this lesson we're going to look at IPv4. We're actually going to do a couple of objectives here, actually part of 1.8, configure, verify, and troubleshoot IPv4 addressing. Subnetting I'm going to do as a separate segment, and I also am going to provide a number of videos that I've done previously to support classes on how to subnet. A couple of different ways, one writing everything in binary and the other one using what we're going to call the increment, and we'll talk about that when we do the subnetting. So we're going to do configure, verify, and troubleshoot IPv4 addressing and describe the need for private IPv4 addressing in this one. So IPv4 address, the structure, classes, we're going to have classes of addresses, and then the private addresses. In IPv4 addressing, it's a 32-bit number, and it's called DDN, dotted decimal notation, and dotted decimal because we have decimal numbers with dots between them. Each of the numbers is 8 bits, which means that 2 to the 8th is going to be 256. 0 to 255, and you got to remember that in the world of networking and IT, 0 represents something, not the null set. So what we got here is the dotted decimal notation 192.168.16.3.1, and then the binary notation, and we're going to look at just in a second how to do this particular conversion. So when we talk about this thing, it is a, if I can get my pen over here maybe. Okay, pen has been found, I think. So these are layer 3 addresses of the OSI model, and then we would be what, layer 2 of the TCP model. Every network interface needs an IP address to send and receive packets. So in order to send and receive packets using the TCP IP protocol, we have to have these addresses. 32-bit number, DDN is used to write them, and that's for us. Each group of 8 bits, an octet, so each of these is an octet. We have 4 octets in this thing. Is converted from its binary to decimal form and separated by dots, and the dots again really are for us. The decimal range 0 to 255, which equals 256 numbers, because again 0 represents a placeholder in this thing. 192.168, I keep saying 168, 192.168, and you'll see when we get done, I've used it so many times, it's a private IP address. 192.16.3.1, I did 16 because it's a lot easier to convert than 168, is an example of an IP address written in DDN, dotted decimal notation. So we have that thing. How do we get this dotted decimal notation converted to binary? Because computers are going to use the ones and the zeros. We know that they use ones and zeros. In the beginning, they tried actually using base 10, but the voltages became unstable. Binary has a voltage or doesn't have a voltage, on or off, so it's a lot easier to discern what goes on with it. There are a couple of different ways. We have this chart here, 2 to the 0, 1, 2, any number to the 0 power is 1, and these represent the value of each of the placeholders. So we start with 1, 2, 4, 8, 16, 32, 64, 128. And this one here, this is how we get 255 when we start with 0. So this column 1, if we have the values that are available to it, can be a 0 or a 1. A 0 if it's turned off, a 1 if it's turned on. Column 2 can again have a 0 or a 1, which means that if we have these 2 bits, and I'm not going to go very much farther because it gets to do the illustration, it gets kind of weird, but here we can have a 0, 0, 0, 0, 1, 1, 1, 0, which is going to be 2, and then 1, 1, which is 3. So we have 0, 1, 2, 3. 4 values represented by 2 of these. When we do the whole thing, we're going to get 256 values, 0 to 255. And the 255 is because this one over here, when it's all ones in here, it's going to be set to an odd number, obviously, because it's going to have a 1 added to it. Everything else is even, as you'll notice. And the, I guess, advantage to binary is all you got to be able to do is multiply by 2 when we do these things. So we can use this chart in order to add things up. The other way here, I say subtraction method. Let's say that we have a number 200. 200, when I go into that, I say, look in the first one here, 128, and when you do conversions, I recommend that you just write this stuff down, 1, 2, 4, 8, 16, 32, 64, 128, so that you have these values. So we'll go in here and say, 128, is 200 greater than 128? Yes, it is. So we would put a 1 in that spot and subtract 128 from it. I say it's going to be what, 2, 9, take away 2 is 7. Did I do that right, I hope? 8, 2 is 10, 7, I'll carry 1, 10, yeah. 72, is 64 greater than 72? Yep. So then we subtract 64 from it and we get an 8. Is 8 greater than 32? Nope. 16? Nope. Is it greater than or equal to 8? Yes, 1. So, and then everything else would be zeros. If we add up 128, 64, and 8, we should come up with 200. So 128 plus 64, right? Plus 64 plus, what was it, 8? 8 and 8, 16. 4 is 10. 0, carrier 1. 6 and 3. See, 8 and 4 is 12. Did I mess that up? No, I just can't add. 8 and 8 is 16. 20. So if we carry the 2, it'll work a lot better, huh? 2, 4, 10, and carry a 1, and we get 200. So we can either use the chart, add them up, or use the subtraction method in order to convert from decimal to binary. If we have the binary, obviously we write it in binary here and just add up the digits to get the number that we want. What we've talked about in the past is that to be delivered, we have to use a layer 2 protocol, a data link layer protocol. And over here in the straight lines and the dashed lines, and this is packet tracer images, are going to be a LAN, a local area network. And the primary protocol that we're going to use there is Ethernet. And that's what we say here. Encapsulate the IP packet in Ethernet. So we have, coming down the stack, we have our IP and the layer below it, layer 3, and we go to layer 2, we're going to encapsulate it into Ethernet for the Ethernet network. When we get to the router here and we go out over a serial connection and an HDLC here, it's transport layer, not transport, data link layer. HDLC is going to be a data link layer protocol that we use on serial, and we have these little lightning bolts here that's going to represent a serial connection. The cloud obviously is going to be the internet or the cloud that we're going within our own enterprise. So what we have to do when we get to the router is to change from a LAN to a WAN. So what happens is we extract the IP packet and encapsulate it into the wide area network, into the WAN protocol, in this case HDLC, which is the Cisco proprietary. When we get to the destination here, we extract it and then encapsulate it in Ethernet again to get it delivered to its destination. So encapsulation, as we go down the stack, either the TCP/IP or the OSI model, we're going to wrap the information. We start out with the data and on down the stack, and then add header information to it in order to get that data delivered to a specific location, and that specific location we know is eventually going to be a MAC address. So we're going to move it down the stack from one location to the other. The IPv4 header, what does it look like? And in here we're going to have some specifics. Version, and this one is going to be 4, obviously. IPv6 header is going to be a lot different. We're going to look at it. The length, header length, type of service. These are going to be specialties when we get to quality of service. We're going to mark these things, and then again a length in here. Identification, any flags that have been set. Fragment offset if it's fragmented, and we looked at one of those, I believe, in a Wireshark configuration. When we fragment a packet, and most of them are marked "Do not fragment." Do not fragment. If we do that, it just tells the system where in the information and the header information how deep it's going to be. So if we have fragments, it just tells us where that fragment starts. So it says, okay, start at this location for this fragment, at this location for this fragment, and this is what allows somebody to insert surreptitious, I guess, information, hack our system. And then we have the time to live. We talked about that with traceroute. It uses the TTL, the time to live, and we use this in order to make packets eventually go away on the internet, so that they won't live forever. And the protocol here is going to be the next protocol, and here we're basically going to have TCP or UDP. Those are the ones that we use today. The checksum, the header checksum, goes in here, and when it gets to the destination, checksum is recalculated compared to see if anything bad happened en route. And then we have the source and destination address, and they're going to be, again, 32-bit addresses in IPv4. So a little quick look at the IPv4 header here. IPv4 addressing, and we're going to look at the unicast, broadcast, and multicast separately. It'll be a relatively short one, but the addresses themselves are broken up into classes. We have Class A, Class B, and Class C. The difference between these is how many networks, and we have a network and a host portion, and each of them has a network and a host portion. How many bits are part of the network and how many bits are part of the host. The Class A networks go 1, the network addresses go 1 to 126. They would actually go to 127, but 127 is reserved for loopback. 127.0, well, let's do the whole thing. 127.0.0.1 is the loopback address used for troubleshooting. So it is a reserved address. A Class B network has 2 octets as part of the network address and 2 octets as part of the host. The hosts are the addresses that can be assigned to an individual entity, a computer, a printer, server, router, switch. A device is going to get a host address. So the network address would be the same for everybody that's on all of the hardware that is on the same network, and the host addresses have to be unique for each of these. How do we know how long the network address is? That's the subnet mask. And the subnet mask is an entity that once we start it, and 255 is all ones. 2, 3, 4, 5, 6, 7, 8. You can add that up and get 255. Go back to the chart on the values, or write down the values, the placeholders. 255. Once we start with ones in the subnet mask, they have to be contiguous ones until we get to the end. We cannot mix. A subnet mask can't look like this. it has to have all ones. And then once it gets to all ones, it's all zeros. So every part of the subnet mask that is ones is network, and every part that's zero is host. So we have a network portion and a host portion. And the class C has got in its network, it is spelled, I'm consistent anyway, in its network has got 3 octets for the network address and 1 octet for the host address. So the range of addresses, class B 128 to 191, class C 192 to 223, and then we have some that multicast, and we'll talk about what these are. Here an address identifies a subset of nodes. It's going to be a grouping of addresses. 224 to 139 and 240 to 255 are experimental. These are the ones that we can't use. The ones that we can use, that we can get addresses for and assign to hosts, are the A's, the B's, and the C's. And we need to talk about these before we actually talk about subnetting, because subnetting is when we're going to take these large class full networks, and we're going to break them down into smaller components, because we may not need something that has 65,000 addresses in it. We may need fewer. And in this one we're going to have 256 total, but we're going to have 2 special addresses. One's called the network address, and the network address is the one where it's all zeros in the host. So it identifies the network. And the other one's going to be the broadcast. And we'll talk about broadcasts again separately, but the broadcast address is the one that's all ones in the host. Broadcast goes to all of the devices that are in that particular network. So class full, class is, and then we're going to have, we're going to call it CIDR, classful internet domain routing, which we're going to start with a class, and then we're going to change the subnet mask in order to have network addresses, the number of network addresses or networks the size that we need, not the ones that are predetermined. So the network address, all zeros in the host. The broadcast address, all ones in the host. Unicast address goes to a single entity. So we have unicast, broadcasts, and multicasts in IPv4. This is another chart on the classes. We can look at what they are. Class A 0 to 127. 127 is reserved for loopback. And then the default subnet mask /8, 8 bits, 255.0.0.0 is going to be it. The number of possible networks, 2 to the 8 minus 1, 128 networks, because we're not using 127 in these things. The number of hosts per network, 16,777,214. And we'll talk about private IP addresses here in just a minute, but private IP addresses are the ones that we can use for free. Public IP addresses we got to pay for. So it's going to be the whole 10 network, and then the Class B networks, 128 to 191. If we look at the binary of these things, a Class A would be 0, would begin with a 0. A Class B will begin with a 1, 0, whatever. 127 here. 128, 0. We'll get there. 0, 1, 2, 4, 8, 16, 32, 64, 128. So it starts with 1, 0. A Class C starts with 1, 1 when we add the 128 and the 64. Class A, B, C, D, and E. If you get into a situation that you need to calculate them on a test, for instance, and when you do a test, when you may need these, or you probably will need these. You will need these. Go ahead and write down the sequence before you actually start the test, because you're going to have a little bit of time and a scratch sheet when you get ready to do these things. 127, loopback address. 169, link local address, also called an APIPA, an automatic private IP. This is actually a Microsoft innovation here, and what it says is that I'm trying to get an automatic address, a DHCP address, and there's no server available to give me that information. So I'm going to assign it to me myself. So it's a 169 address with a 16-bit mask, which is a 255.255.0.0, and it also won't have a default gateway. No, we haven't talked about that yet, but we will. You probably already know what that is anyway. Private IP addresses, and we saw them in the previous slide. A range of addresses that organizations can use to build an internal TCP/IP network. Why do we need these things? IPv4 has a limited number of addresses, and we have run out. All have been issued. Doesn't mean they're all in use. It means they've all been issued. What the private IP addresses do are defined in RFC 1918. If you see that, RFC 1918 is private IP addresses. What that allows us to do is a process called NAT or PAT, Port Address Translation, Network Address Translation, which means that inside of our network, and we have our router here, our firewall, and we have our protected network or our private network back here. We use private addresses back here, and then when we get to the public network, we translate the private to a public address if we have a one-to-one translation, so that we don't have to have, if we have 300 users back here and all of them are going to be on the internet at the same time, we may have 100 addresses here. Or if we really want to do it, we can use a thing called NAT, Network Address Translation. We talked about sockets when we were looking at the OSI model, which is an IP and a port number. So we can have an IP address, our public IP address, and a port number, and we have 65,536 port numbers, so we can associate that with a port address translation and only have a single IP address and a whole bunch of ports that we can go to the internet on. So what this has done is gives us some privacy, some security on our protected network, and it has also extended the life of IPv4 addresses, so that we can now have relatively large private networks without having to buy or expend the public IP addresses. 3 categories. The class A is the entire 10 network, 10.0.0.0 to 10.255.255.255 with the subnet mask of 255.255.0.0.0. Class B's, not as many addresses are available. 172.16 through 172.31. And it's equivalent of 16 networks that we use here, and we're going to use a different subnet mask, and when we do subnetting we'll talk about how we do that. And then the class C's, this is the class B, the class C's are 192.168.0.0, the whole thing to 192.168.255.0, the equivalent of 256 networks. We actually mask it 255.255.255.0, subnet mask, subnet mask, subnet mask, host addresses. So we can have 0 to 255 networks here, and we can have 0 on each of those networks. We can have 256 total addresses, 254 usable addresses. We can't use the network, and we can't use the broadcast. So not assigned for use on the public IP network. You should never see these on the public network, and they've extended the IPv4 life expectancy. We also get some security because we can have on our private network an addressing scheme that's not publicly available. So we get both security and life extension of IPv4, which may or may not be a good thing. So in summary here, we talked about the IPv4 address structure, the dotted decimal notation, how to convert DDN dotted decimal to binary. We talked about classes, and we talked about the addressing, the subnet mask, how the subnet mask works in the classes, as well as private IP addresses, the value of them, what they do for us in the extending the life of IPv4, the address space, as well as how it provides security to our private network by using network address translation or port address translation. The next thing that we're going to talk about is subnetting, and again we're going to discuss it a little bit, and I have provided a number of videos that I've done previously on how to actually use subnetting, how to do subnetting. So there will be the theory of it, and then a number of videos on how to do it in a couple of different ways, writing it out in binary or using a magic number that we'll talk about. Hope to see you there.